Hi, this is an example you might like to try. It involves differentiation. We're given that k of x equals e to the power x over 5, and it's all divided by the square root of 2x squared plus 10x minus 17. And we're asked to find k dash of x. In other words, to differentiate k of x with respect to x. Now the first thing I notice here is that I've got two functions of x being divided by one another. And we should be familiar with this kind of result. Let's say we've got y equals u over v, where u and v are functions of x. Then to differentiate this requires knowledge of the quotient rule. A rule that you should be familiar with, but just as a recap, dy by dx always equals the bottom of the fraction, v, times the differential of the top of the fraction, that's v du dx, minus the top of the fraction, that's u, times the differential of the bottom of the fraction, that's dv dx. And all this is divided by the bottom of the fraction squared, so in other words, v squared. And as I said earlier, this is a rule that you should be familiar with, the quotient rule then. You generally find it in most formula books, but certainly worthwhile learning. Okay, well, in the example that we've got here, u, the top of the fraction, is e to the power x over 5, and v is the square root of 2x squared plus 10x minus 17. So if we're to start to find k dash of x, let's just write it down here. We've got, therefore, k dash of x is going to equal, well, it's going to be the bottom of the fraction multiplied by the differential of the top of the fraction. So the bottom of the fraction, we'll just write in here, that's going to be 2x squared plus 10x minus 17. And that is all square rooted, but I'm going to change the square root to the power a half. Again, we should be familiar with that. Now we have to multiply it by differential of the top of the fraction, and the top of the fraction is e to the power 1/5 x. I know it's got x over 5, but we can think of that as e to the power 5th x. And this is a fairly standard result, one that again we should know. We should be familiar with differentiating functions of the form y equals e to a constant, let's call it a, to the power x. dy dx by the chain rule turns out to be a e to the power ax. So that's another rule that, as I say, you should be familiar with. And again, you generally get this kind of result in most formula books. So when it comes to differentiating the top here, it might say e to the power x over 5, but we can think of this as e to the power 1/5 x. A is a fifth. So multiplying this by the differential of e to the power x over 5 is going to be 1/5 e to the power a 5th x, or just simply x over 5. I'll put that in brackets for the time being. Okay, so that's the first part, v du dx. Now we've got to do the next term, minus, and then we've got the top of the fraction, u, times the differential of the bottom of the fraction. So u, the top of the fraction, e to the power a 5th x, or e to the power x over 5, and that's now multiplied by the differential of the bottom of the fraction. Now for this, we've got to use the chain rule. We've got to see this as, say, y equals 2x squared plus 10x minus 17, and it's all to the power half. Now if I let t, let's just say let t equal 2x squared plus 10x minus 17, then we can see this as y equals t to the power half. So therefore y equals t to the power half. So when it comes to working out dy by dx, we use the chain rule. Dy dx is the same as dy by dt multiplied by dt by dx. Now, for dy by dt, differentiate y with respect to t, we're going to get a half t to the power minus a half. But t is 2x squared plus 10x minus 17. So when we do dy by dt, we're going to get a half, okay, t to the minus half. So t is 2x squared plus 10x minus 17, and that is now to the power minus a half. And we need to multiply this by dt dx. We need to multiply it by the differential of t with respect to x. So if we differentiate t with respect to x, we're going to get 4x plus 10. So we'll put this in brackets. We can just squeeze it in here. 4x plus 10. Okay? So that is the last term there. Now this is all divided by v squared, the square of the denominator there. So just draw one long line, and that is over the square of the denominator. So if we square the square root of 2x squared plus 10x minus 17, all that happens is we get rid of that square root. It becomes 2x squared plus 10x minus 17. Okay, so that's it essentially done, differentiated, but it doesn't look very tidy. So when we have things like this, we need to tidy it up. And if we look at the first term, let's tidy this up as 1/5 e to the power x over 5, or e to the power x over 5 over 5. That would look a lot better there. Multiplied by 2x squared plus 10x minus, no, not minus, yes, minus 17, sorry, minus 17 to the power half. So that's the first term tidied up. Now this second term here, if we tidy it up, we've got this power minus a half. So that's the same as 1 over 2x squared plus 10x minus 17 to the power half. And so we can rewrite this as e to the power x over 5 multiplied by 4x plus 10, and then we've got the 2 here multiplied by 1 over, as I said earlier, 2x squared plus 10x minus 17 to the power half. So that actually ends up down under here as 2x squared plus 10x minus 17 to the power a half. And all of this is over 2x squared plus 10x minus 17. And I would always tidy up each term when I'm using the quotient rule. So that's what I've done here. Okay, tidy up each term. Now we need to get rid of these awkward fractions. I'm just going to highlight them in red. We need to get rid of the 5. We need to get rid of the 2, and we also need to get rid of the 2x squared plus 10x minus 17 to the power a half. And to do that, I need to get rid of the 5 and the 2 by multiplying by something that goes into, that 5 and 2 go into, and that is a 10. So I'm going to multiply top and bottom by 10, and also by 2x squared plus 10x minus 17 to the power half. So what is that going to give me? Well, if I multiply first of all by 10, can you see that 5 would go into 10 twice? So I would get 2 lots of e to the power x over 5. Remember, I'm also multiplying by 2x squared plus 10x minus 17 to the power half. When I multiply it with that one, then the powers are added, and I just simply get 2x squared plus 10x minus 17. Okay, so I multiplied this term then by 10 times 2x squared plus 10x minus 17 to the power half, resulting in this. Now I do the same to the next term. So when I multiply by 10, the 2 will cancel into 10 and give me a 5, so I'll get 5 e to the power x over 5. I'm also multiplying by 2x squared plus 10x minus 17 to the power half, so this will get cancelled and just leave me with the 4x plus 10. And now all of this is divided by, and remember I'm multiplying top and bottom by 10 lots of 2x squared plus 10x minus 17 to the power half. So I'm going to get a 10, and then I'm going to get 2x squared plus 10x minus 17 to the power 1.5, or 3 over 2. Okay, so we've got that far now. What I need to do is carry on and just try and simplify this further. So I can see that we could pull out, say, e to the power x over 5. Let's do that, e to the power x over 5. And then I'd want to put a square bracket up, and inside here would go the 2 multiplied by 2x squared plus 10x minus 17. Oops, that didn't look good, so I'll just put minus 17 back there again. Okay, now when it comes to second term, I would want to have a 5. We've already got the e to the power x over 5 out the front, and then we just need the bracket 4x plus 10. Okay, and then close the square bracket off, and all of this is divided by the 10 and 2x squared plus 10x minus 17 to the power 3 over 2. Pen doesn't seem to be writing that well at the moment, so there we go, to the power 3 over 2. Now I need to clean up what we see inside the square bracket. Never leave anything inside a square bracket. So I can expand each of the brackets in here, so I can reduce this square bracket now to a curved bracket, and I get 2 lots of 2x squared, which is 4x squared, 2 lots of 10x, that's 20x, 2 times minus 17 is minus 34, and then for this bracket we got minus 5 times 4x is minus 20x, and minus 5 times plus 10 is minus 50. And again, all of this is divided by 10 times 2x squared plus 10x minus 17 to the power 3 over 2. Let's just scroll up again. Now we could group up the terms inside the bracket here, I'm sure. So we've got e to the power x over 5. And what have we got? We've got 4x squared. That's just 4x squared, the only x squared term. We've got 20x, now take 20x, so that goes to 0. And then we've got minus 34 minus 50, so that's going to be minus 84. And again, that's all divided then by 10 lots of 2x squared plus 10x minus 17 to the power 3 over 2. Now for this bracket here, I notice that 4 is a common factor, so I could bring 4 out the front. 4e to the power x over 5. Pulling 4 out leaves me with x squared minus 21. And that's all divided again by 10 lots of 2x squared plus 10x minus 17 to the power 3 over 2. Now I can see that the 4 and the 10 have a common factor. 2 goes into both 4 and 10. 2 goes into 4 twice. 2 goes into 10 5 times. So it looks as if we're now getting to the end of this question, because if we just move this up a bit more, I can see that therefore, let's just put back k dash of x. K dash of x equals 2e to the power x over 5 multiplied by x squared minus 21, all divided by, whoops, again, it's not working out very well, all divided by 5 times 2x squared plus 10x minus 17 to the power 3 over 2. So So that's essentially it. There can be different versions of this, I'm sure. I mean, you could write that denominator in another way. You could write it as 5 times, say just the square root. That 2 there would be the square root of 2x squared plus 10x minus 17, and then you've got that all cubed to the power 3. So that's one way of doing it. The top stays exactly the same. You might find that you could put e to the power x on 5 at the rear of this bracket. It doesn't matter, okay? But there's another option for that. That square root doesn't look particularly good, but there you go. That's a better square root, I hope. So, you know, a couple of versions there. I hope that agrees with the answer that you've got to find. And there we go. Okay, so I hope that's been of some use. Do let us know if it's if there's any problems in trying to understand what I've done. Oh, and by the way, let's just scroll back again, because I can see that this business up here is a bit awkward. I'll just quickly run through that again. What I did was times top and bottom by exactly the same value, and I chose a number that 5 and 2 went into, which was a 10. Let's just write it in green here, a 10. And then I also multiplied it by 2x squared plus 10x minus 17. We'll just squeeze this in here, sorry about this, to the power 1/2, okay? But I must do the same to the bottom, okay? 10 times 2x squared plus 10x minus 17 to the power 1/2. I can do this because this divided by this is 1, and if I times anything by 1, it doesn't alter the value of the fraction, but it will change the appearance of it. And so you can see, just once more, the 5, when I took this term here and multiplied it by the green part here, the 5 went into the 10 twice. So that's my 2 there. I get e to the power x upon 5 times 2x squared plus 10x minus 17 to the half times the green 2x squared plus 10x minus 17 to the half. So you add the powers, and that's why I got 2x squared plus 10x minus 17. And then when we came on to this term, you can see the 2 cancels into the 10 5 times. That's why I got that. And then you've got e to the power x upon 5 times 4x plus 10, and the 2x squared plus 10x minus 17 to the half cancelled out with the 2x squared plus 10x minus 17 to the half here. Okay, so I had to multiply this green bit by each of these 2 parts because there's 2 terms here. And then I had to multiply the denominator by the green one, and that's why I got the 10. And I added the powers for 2x squared plus 10x minus 17. So this is power 1, this is power to half, so I got to power 3 over 2. And then, as I say, the rest just followed on from there, just tidying it up. Okay, so a bit cramped, but as I say, I hope it's given you some idea. Okay.